Yes, we're starting a whole new topic, and I'm hoping the sound is working. It seemed to work okay last time. RC Cola. The reason I have RC Cola up there, go ahead and grab a worksheet. RC Cola has to do with matrices. We'll come back to that. But just think of the taste, the fizz, the sweetness of RC Cola. My algebra teacher, actually, he was not my algebra teacher, but he was the other algebra teacher in high school that had the computer in his lab. And of course, me being the nerd, we'd go play on the computer. And back then, the computers were just starting out, hardly anything to speak of compared to today's computers. But that was the nerd hangout. And that algebra teacher, he was a fun guy. And when we talked about matrices, he said, yeah, remember RC Cola. And we'll see that connection in a second here. In Moodle, remember you have this section that we're in right now, week 13. There's only one more section after this. We're going to just do a little bit more in matrices next week. I'm hoping you'll find matrices are pretty easy. It's just another way of looking at numbers. There are some rules we want to learn about matrices, but I'd say it seems that it's not as, say, abstract as logarithms and solving problems with logarithms. But we'll come back and help you review for the final, which is planned to be mostly over the last section, but there will be some things from previous sections in the final quiz. But mostly from this last section, exponents through matrices. So let's take a look at what matrices are. And I think if I close this, my recording will not have as many problems. I have keep as many things closed as possible. Things seem to work better. So I'm going to close that tab. Oh, before I close that tab, remember up in course resources, you have extra help for all the topics under course resources. And way towards the bottom of course resources, there is some more text. I actually have that text. And there's also a video. I'm not going to play the video, but that might help you through. And remember, you can go to YouTube and just do search on matrix algebra, and you'll find thousands of videos. You might find just the one that made it click for you. Here's what you have for a worksheet. And my thought is, let's go through this worksheet. And you'll be doing matrix math without really knowing it. Let's just go through this practical example of this soccer team that has some equipment that they like to, it's a soccer league. They have some equipment they'd like to order for next year. We've got two teams, the Wildcats and the Mudcats, and they realize they need 6 goals for the Wildcats, 10 for the Mudcats. And they have some soccer balls they need for that team, some jerseys as well. So that is something you might see in a spreadsheet. So matrices, although in algebra, they primarily use them for solving systems of linear equations. That sounds pretty scary. But in real life, there's matrices out there all the time. You just don't know it because we don't call them matrices. We just call them a spreadsheet or a listing of something. But let's just look at how we would solve this in a practical way without even thinking that we're doing matrix stuff. We have the cost per goal over here, cost per ball, and cost per jersey. And we have the equipment needs for Wildcats in that same order, goals, balls, jerseys, the same order over here, matching the cost per goal, per ball, per jersey in this table. So let's just take these numbers, the number of goals, balls, and jerseys for each team, and let's write them down below in this little table. It's a matrix, but we're not going to call it a matrix. Let's just call it a table of the needs for our team. So 6 and 30 go ahead and grab a worksheet. 6 and 30 and 14. That's the needs for goals, balls, and jerseys for the Wildcats. And the goals, balls, and jerseys needed for the Mudcats, 10, 24, and 20. So we're simply taking that table and throwing away the headings, just keeping the numbers because the numbers are what we need to do calculations on. Later on, we'll come back and realize, oh yeah, those numbers apply to different columns. Okay, so this is what we're going to call our matrix E. But we'll just treat it, this is remember how it applies to this particular problem. It's just the number of goals, balls, and jerseys that league needs and that this league needs. Now over here, we're going to take away the headings and just put the numbers in. We're going to call it our cost matrix or our cost table. And the cost then is just 300, 10, and 30. So we just turned a table into a matrix. But before we do any math on these matrices, let's examine what we have here. We have over here a table that has 3 rows. And and it also has 2 columns. Since it has 2 columns and 3 rows, we call it a 3 by 2 matrix. Also known as the order of the matrix. The order of the matrix is 3 by 2. That's where we came up. That's why I had this image up here. RC Cola. Row columns. The number of rows times the number of columns, or by the number of columns. You go row column when we talk about the order. RC Cola. Row column. How many rows? 3. How many columns? 2. So it's a 3 by 2. RC Cola. Think to yourself, RC Cola. For arrays, we always keep track of rows by columns. In the book, I don't know why they chose these 2 letters. They choose to use the letters M by N. Like, really, that doesn't help me remember that. Maybe in Latin it means rows and columns. But to us, it's just 2 letters that look a lot alike when they're small. But they use M and N a lot, but all they're referring to is the size of that matrix. Now over here, looking at this matrix. This is our cost matrix. What is its order? How many rows? It's a 1 row. How many columns? 3 columns. So 1 row by 3 column. Now what we'd like to do for our final result in this practical problem is figure out what is the total cost to each team if they're going to get the equipment that they need for next year's league. Well, let's do the multiplication, and then we'll go back and do easier stuff. So I'm going to do this, walk you through this, and then we'll see that we can actually do simpler things with arrays, with matrices. And I'm hoping that by seeing this practical example first, it's like, oh yeah, that's all making sense. Let's see how we can make sense of this. We're going to take our cost matrix, which we typically write with square brackets, and then our 3 numbers in our cost matrix, 300, 10, and 30. And we're going to multiply it to get the results we need by our column, by our 3 by 2 matrix that has those costs of equipment in it, 6, 30, 14. And sometimes when they write this out, they don't even have commas in here, but I like to put commas to make it clear that those are 2 different numbers, 6, 10, 30, 24, 14, and 20. Now let's just think about how we would actually calculate the total cost for each team. Well, we're going to multiply out how many goals we need by how much goals cost, and multiply by how many balls we need by how much balls cost, and how many jerseys we need by how much jerseys cost. So let's multiply this out. We're going to get an array of 300 times, that's the cost of goals, times 6 goals. And we're going to add it to 10 times how many balls that we need, 10 times the number of balls. And we're going to add it also to 30 times the number of jerseys that we want to buy. And adding those together will give us the total cost for the Wildcats for next season. Now, I'm not going to do the calculation. I'll do that when I come to fill this in. Let's see how we did that calculation. I multiplied 300 by that. Let's see, I'll do a little, too many lines here might confuse you. I multiplied 300 by that first thing, because that's the cost of that. I multiplied 10 by the cost of by the number of I need. And I multiplied 30 by the number of jerseys I need. So see how 3 numbers here got multiplied by each of the 3 rows here. And then the total cost for the Mudcats, well, I multiply 300 times how many goals they need, 300 times 10, and I add to that 10 times the number of balls that they need, 10 times 24, and I add 30, the cost of jerseys, times the number of jerseys they want. They want 20. They have a little larger team. Now this ends up just being what size array? 1 row by 2 columns. 1 by 2. And now let's just do the math quickly here. Let's see. 6 times 300, that's 1,800. So let's just do the math down below. 1,800 plus 10 times 30 plus 300 plus 30 times 14. Well, that's 30 times 10, 300, plus 30 times 4, 120. So that becomes 420. Oh, we won't draw past the end there. Well, I guess 420. And gives me a total of 2,100, 2,520. Don't worry about the addition as much as how we got there. We multiplied the 300 times how much that item costs, 10 times that item. And now let's do that other one here. Let's see, that might be a little easier there. So it's 300 times 10, that's 3,000. A few more goals for them, plus 240. Plus 600. A little easier calculation for them. And that gives me 3,840 for their total cost. By going through this practical example, you have done matrix multiplication. Something that we're not really going to be doing until next week. But I wanted to just show you that you're using matrices when you're solving some practical problems like this. But we're going to back up and actually do easier things with matrices first. Just throw this practical problem at you of, hey, matrix, we're doing actually matrix multiplies, but we're solving a practical problem of, hey, what's the total cost for next season for each of these teams? Well, we did it by multiplying one matrix by another. One other question that we have is, well, next year the costs are going up 100%. when you see it up by 100%, the easiest way to think of that is the costs are doubling next year. It's going to be the same cost, but another of the same cost. So increase by 100% means we're doubling. So what we do, figure out if this is the cost for this year, next year's cost, is going to be 2 times the current array total cost over here. And this is what we call scalar multiplications. I'm just doubling everything in that array. We call this scalar multiplication. This is an array, a 1 by 2 array. Scalar multiplication means multiply everything in that array by the same number. And in this case, I'm going to get 5,040. And let's see, that's going to be 7680. Just multiplying everything in there by 2. That's scalar multiplication. And they're going to do that first because multiplying 2 matrices like we did here, that's a little more complicated than, hey, let's just multiply everything in the matrix by some value. So that's the start. Well, that's a example problem that you'll be able to solve and look back and say, hey, that wasn't so hard. At first, it's like, wait a minute, we're doing all these multipliers and these tables of numbers and multiplying one table by another. Yeah, it looks confusing at first, but let's back up and look at it. We'll go back to the basics here and just talk about matrices, and we'll be getting here next week. So this is just giving you a taste of what matrices can do, and it seems like that makes a lot of sense. In algebra, the reason we're doing matrices on the back of your worksheets, they use them in algebra because matrices can solve huge problems. They call them systems of linear equations. Now, you're not going to have to solve huge systems of linear equations. You'll just know that, hey, knowing a little bit about matrices, there's a way to make those huge problems of systems of linear equations be much simpler to solve. And it's actually a pre-calculus concept. I used this in calculus back in college for solving really, really complex things. This really made that hard stuff a lot easier. They're giving you an introduction to matrices just so you know, hey, this idea of matrices can really be powerful in math. Not that you're going to use everything. I don't know if I used all my calculus stuff, but being a nerd, I just loved studying it. It did come up here and there. When you get to really hard problems, you go back to your toolbox and say, oh yeah, matrices will help me solve that. So that's why they're having you learn this in college algebra, because out there it will help solve, or the scientists use them to solve really hard problems. So knowing about them, they want you to know about them. So let's go now back through some simpler concepts. Now that we've seen what arrays can do, and work through an actually not super complicated, but a little harder problem. Let's go back. Let's take a step back and work through matrices. Instead of multiplying, we'll start out with some easier things. Adding and subtracting is a lot easier. And there's our little example of the soccer team, the Wildcats and the Mudcats. They mentioned that problem at the start. That's why I brought it up as well. But they didn't say much about it. They just say, oh yeah, matrices will help us solve this problem. I wanted to kind of think through, okay, here's what they mean, how matrices help you solve that deal with the soccer teams. And before we even do any math with matrices, they go back and say, let's remember what a matrix is. It's simply a rectangular table of numbers. Remember we talked about the order of the matrices? To describe this matrix, let's turn on my pencil. To describe this matrix, how many rows and columns are by C? Here it's 2 rows, 1, 2, and 2 columns. So this is a 2 by 2 matrix. The numbers in there just represent perhaps some numbers in a linear equation, but you don't have to worry about that yet. Let's just worry about dealing with matrices. Then we'll see how they solve hard problems. Here we have matrix. Notice they don't put the commas in here all the time. They just put a large space between the numbers. So this is a, how many rows? 3 rows. 1, 2, 3. By 3 columns. 1, 2, 3. So this is a 3 by 3 array. Probably the most popular size of array they'll be using when we deal with matrices. A 3 by 3 array. This one here, 3 rows, 2 columns. Remember RC Cola. 3 rows. It's a number of rows. 1, 2, 3. And 2 columns. 1, 2. So 3 by 2. They love to give you the full description in this M by N matrix and even give each element in the matrix an address. So it looks confusing, but all they're saying is, let's keep track of the location of every item with these little sub numbers. Again, those go in the order of RC. See how everything in this one is on row 1. Therefore, we have 1 in the front of every sub-index Aij. It's the way the mathematicians write the general form of a matrix. This comes out useful when they start doing formulas of matrices. For us, we're not going to use them so much, but they want you to see that, yeah, we address every item in my array. Think of that as a little address or location. 1, 2 means row 1, column 2. Row 1, column 3. We don't call that A13, although that's what it sure looks like. We call that element at row 1, column 3. That's why they have those little location sub numbers there. Now they're using I's and J's. Not only do they go M by N's for how many rows and columns, those mathematicians like to throw an I and J in there as well, just because those are common numbers to say, well, those are like counting variables. For me, when I'm writing programs that deal with matrices, I like to use row and column. I don't know why the mathematicians didn't just stick with rows and columns, but that's what they're like. They like to use different letters, maybe just to because somebody decided back then, and they don't want to change all the books and start using rows and columns. I'm sure there's some rogue mathematicians out there using rows and columns and getting all the other mathematicians upset. Now another thing we call, when we only have 1 column or 1 row, we like to call it if it's 1 row, we call it a row matrix. And if it's only 1 column, we call it a column matrix. So row matrix, the only thing special about a row matrix, it has only 1 row. And a column matrix only has 1 column. That's just some of the terminology they like to use around matrix math. And there it comes back, the 1 by n columns, 1 row by n columns. I think when you see 1 by n, remember RC Cola, 1 row, n columns. RC Cola coming back all the time. Taste the fizz of that RC Cola. So column matrix, row matrix, just some terminology. They're going to be used regularly as we get more complex things to do with matrices. But before we do anything complex, we're just going to do some simple things. I can get my browser to behave for me. We're going to just look at finding our dimensions here. I don't know. I wonder if it's because I'm recording that it gets a little jumpy like this. I'll have to check my drive. Maybe my drive is getting too full. So, there's going to be some basic questions about arrays. You look at this one. What's our dimensions? 3 rows, 3 by 3. Yeah, most popular. So the dimensions, 3 rows, 3 columns. So we call it a 3 by 3. The order of the array is 3 by 3. That's another term they'll use. And the addressing. What are the entries at address 3, 1? Row, remember that's row 3, column 1. So row 3 down, column 1, there is A31. A31. That's that guy right there. A22, well, that's row, or here's column 1, 2, 3. Row 1, 2, 3. And that would be row 2, column 2 right there. I get my pencil to catch up. And so the answer would be A22 is this guy. That's his address. So A22 is 4, A31 is 3. So A22 is 4, A31 is 3. Now this is a lot to come at you right away dealing with matrices. So think carefully through it. We can do some practice now. Let's just do a little practice on this because I know it's not always obvious why are these mathematicians doing all this. Remember, that is our columns and these are our rows. So, just for a little practice, what is the value of A13? Yeah, row 1, column 3. A31. Oh, we've already did A31. Sorry, that's number 3. And A32, column 3, or row 3, column 2. Oh, yeah. See, I almost messed up the row and column. Row 3, column 2 would be 1. So practice with that as we look at arrays. Now 3 by 3, when you have a 3 by 3 is since if row and columns are the same, guess what they call it? They call it a square array. The rows and columns have the same dimension, also known as a square array. Square arrays are special in many ways, just like squares are special. So now that we know what arrays are, how we address the things in the array, now let's do some math with arrays. We've already done some math, but we're going to go back to simple math with arrays. We can add and subtract arrays. Now they like to, remember how they gave you that the row column format of naming the arrays? Think of this as every element gets added to the element in the other array that's in the same spot. So I have 2 arrays that I'm adding together. What they mean by this is when I add them together, every element in the array that's at any position, any row and column, gets added to the other array that's at that same location. So I have 2 arrays added together. Basically just think everything in the same place gets added to the next array that's in that same place. So any element that's over here in that spot, to find the addition of the 2, we'll find the number in that same spot in that array, and that gets the 2 things added together. Should have made different shapes there. But think to yourself, this is something at position ij in this array. The same position in this array, they just add together in this result array, no matter what the dimensions are. And when I'm subtracting, the same thing. Any element in that place 1, 1, they just add together across the arrays. And we'll look at an example of that down here, where I'm adding these two arrays together. Let's just do that. Just write out, since we don't have numbers there, we can't do the math. We just say, oh, that's the result of those two arrays. Let's just add those two together. What do I get? Got to give myself lots of room, because the element in this location is the one in the upper left corner there, plus the one in the upper left corner there. So A plus B is going to be A plus E in this position, right? A plus E, because there's my A and there's the E on the upper left corner. The one in this upper right corner is going to be B plus F. See how that? Upper right corner, and next one, C plus G. Lower left corner gets added to lower left corner, and lower right corners get added together. And if this array got any larger, it would just be those same locations, wherever they are in this array, it gets added to the same element in that same location in this array. Now, do you see one rule that we better have when we're going to be adding two arrays together? If I'm going to be adding something in the same position from both arrays, the arrays better have the same order. They can't be 3 by 3 matrix added to a 2 by 2. You can't just say, oh yeah, we just add numbers to the upper two rows and columns. Nope, that's not allowed. If you're going to add arrays together, they have to be the same order, the same number of rows and columns. They don't have to be square. They just have to have the same dimensions, or they can't be added together. Doesn't work the same with multiplying though, but that's for next week. Adding, we just add them. They have to have the same order, and we just add the elements in the corresponding positions. This is going to be becoming something that's very useful, but we skipped over a few rules here because they go back to basic math rules. Since I'm just adding numbers as two tables, kind of just saying, oh, I'm doing a lot of additions all together, the same rules of addition apply. The order of addition doesn't matter because I'm doing addition of every element in the corresponding locations. The associative rule, the order that we do them, adding these two together first and then adding this to it, is the same as adding these other two together and then adding this to it. The associative and commutative rules apply. The order doesn't matter when I'm doing addition, and the grouping doesn't matter as I do addition, because I'm doing just a bunch of additions one by one through each element of the array. So that's what they call, that's the associative rule with arrays when I'm adding and subtracting. Somewhere here they say the rule. They kind of just hide it there. Like dimensions. That's what they mean. They have to have the same rows and columns. Like dimensions. So that has already been told us in that little statement right there. But remember, without being the same size, we can't add them together. And they don't really make a big deal about that. They just, all the problems just work out that way. Okay. Let's do this with just real numbers. Instead of letters, what would be our solution? Adding those two together. You see the answer? Does it pop out at you? Just do it one element at a time, and I'll write it right over here. Upper left corner, 4 plus 5. We're looking for sum, so A plus B. You don't have to do it in your head, but just to help you, I'm going to do this. See how that's 4 plus 5 added together. Gives me 9. 3 plus 0. It doesn't matter the order that you do it either. You can do rows across or columns down, because you'll do 1 plus 9 and then 2 plus 7. catch up to me. 2 plus. So the final answer then would be 9, 10, 10, 3, and 9. And my 10 disappeared on me. Okay. Is it clear why that's the answer? We're going to start out slow here. We don't want to leave anybody behind. Now that's just addition. We can do the same thing with subtraction. We simply have to do it in the right order. Now, difference of A and B, we assume they're asking for A minus B. Watch your signs. Negative 2 minus 8 gives me a negative 10. 3 minus a 1 gives me a 2. 0 minus a 5 gives me a negative 5. And a 1 minus 4 gives me a negative 3. Now I'm just going to start not putting commas in there because I'm not seeing them put in commas. Now, order does matter with subtraction. That's the only thing you got to watch out for. Otherwise, it's just the corresponding numbers. It just becomes a, think of it as a multiple subtractions, everyone subtracting from everyone else. Again, the same size arrays. And one more example here. Where is A and B? Oh, there's A and B. Just a slightly larger array, A and B. Find the sum and difference. I think we can do the sum in our head. Let's try it. Let's put A plus B up here. Just do one by one. 2 plus 6, 8. Negative 10 plus 10, 0. Negative 2 plus a negative 2, negative 4. 14 plus 0, 14. 12 plus negative 12, 0. 10 plus negative 4, 6. 4 plus negative 5, negative 1. Negative 2 plus 2, 0. And 2 plus negative 2, another 0. Addition is usually easier because you don't have to worry about which direction we're going, negative or positive. Lots of zeros show up. And when there's zeros in matrices, just like in regular algebra, when something's a 0, it makes your solution a lot easier typically. Let's do A minus B. Just for practice. Two minus 6, negative 4. Negative 10 minus 10, negative 20. Negative 2 minus another negative 2, uh-oh, that becomes a 0. 14 minus 0, 14. 12 minus negative 12, 24. 10 minus negative 4 becomes 14. 4 minus negative 5, 9. Negative 2 minus 2 becomes more negative. And 2 minus a negative 2 becomes a positive 4. So sum and difference, just a little practice at that. It doesn't get a lot harder when we're doing math or we're doing addition and subtraction. They're starting you out easy. I think you'll find it a little easier than those logarithms, right? Those exponents and things, that's a little more confusing. I'd say think of this as a little less taxing on the brain, but it is a different approach to adding and subtracting numbers. But it's building up into something that actually is very useful. Remember, we can solve those huge linear equations, but we have to start with these basic rules first. Now we just have slightly different arrays. Again, they're not being too demanding on you here in the textbook. we could do a couple of our own, but I think I'm getting a sense that this is pretty easy so far. Find it okay? I don't want to go too fast, but I'm happy to speed up. But let's just do this a plus b. I'm going to just do the same thing. 2 plus 3, 6. 6 minus 6, or 6 minus 2, 4. 1 plus 1, 2. 0 plus 5, 5. 1 plus negative 4, negative 3. And negative 3 plus 3 gives me 0. Adding and subtracting, easy peasy. Corresponding elements. Now, when it's going to be harder is they'll give you matrices with those abstract numbers in them. That everything in A plus B in the abstract form, my pencil catches up here, A plus B in the abstract form is going to be the matrix containing the elements A, I, J plus B, I, J you'll get the abstract solution. What that just means is at every position I and J, A, the value at B in that position gets added to the value of A at that position. So when you see this, don't be scared. That just means in mathematical terms, where they're in the same location, they get added together. But it does look pretty scary at first. Back at the beginning when they showed you this, I remember first time looking through this, it's like, whoa, this looks hard. When they show you all those I and J's in the matrix form. Come on, Mr. Computer. Guess I don't want to scroll too much through this text. It goes really slow. When they give you all those I's and J's, kind of scary looking. But it's ended up, that's not that bad a concept. But mathematically, when they show you it in the IJ format, where did it go? There. Starts looking like that. That's looking a little scarier. But that just means, we just have elements at those various positions. And remember, rows and columns can get huge, but we can still solve them with what we know about matrices. 3 by 3 is about as big as we get in this book, but out there in the math problems, they have huge arrays, and we have computers to do all this adding of all them together. Your Excel spreadsheets are doing this kind of thing. Now, there's one other thing we do with arrays. But we can add and subtract them. We'll get to the multiply in a little bit, but we're going to do the simple multiply first. We convert some data into an array. It doesn't even really matter what the data represents. In this case, we're talking about the costs of, not the cost, the number of equipment, number of computers, tables, chairs needed for different labs. They're not even talking about costs. They're just thinking there's going to be a 15% increase in the amount needed for the lab. Well, we multiply all the amounts we have right now in our little table, treat it as a matrix, and I multiply it by 15%. This is what we call scalar multiplication of an array. Multiplying every element in an array by a number, it's known as scalar multiply, scalar multiplication. Everything in the array gets multiplied by the same amount. And they show in this example, we're figuring out how much equipment we're going to need to add. What's 15% more? They round it up because you don't buy half a computer or a quarter of a computer. So they round all that up to, okay, if we're going to need more than 4, that means we need 5. Whatever amount of equipment that is. And then they do the addition of the two arrays to give you the total amount of equipment needed next year. So what they did is, today's array of number of computers plus 15% more of that same array of computers equals next year's number of computers. Now the numbers, I know what they represent, but mathematically, I'm just adding two arrays together. One got multiplied by a scalar to give me this, but then it just became an addition. So we're doing algebra on, you can think of it as you're doing algebra on boxes of numbers. Instead of one number, I have a collection of numbers that's being held in a little table, and I'm doing algebra on piles of numbers, on containers of numbers. So that's what we call scalar multiplication. And there is the abstract terminology. I have an array with those addresses in them, given that array, and I'm doing a scalar multiplication of it with abstract representation of each value in my array. Whatever values at row 1, column 1, row 1, column 2, row 2, column 1, row 2, column 2. If I'm multiplying it by a scalar, my result is that scalar value C, in this case, gets multiplied by every element in my array. So that's scalar multiplication. Again, a fairly easy concept. Basically, again, I'm just multiplying a chunk of numbers by some value C, some scalar value C. That's all scalar multiplication is. And we can start seeing that, okay, just like we did in algebra, when I'm multiplying something by two things added together, it's as though I multiply each thing separately and then added them together. So that's the distributed property. How I group them works with arrays of numbers when I'm doing scalars and addition. So just like I can do this in algebra with an x and a y, I can do it with a chunk of numbers held in the array A and a chunk of numbers held in the array B. Like dimensions means those two chunks better have the same size or this will not work. Because I have a little number in B that doesn't have a corresponding location in A. Sorry, that won't work. So A and B, again, are the same order matrices. They don't have to be square, but they have to be the same number of rows and columns. And there's my distributive property. So just to practice that, let's just take a look at some simple scalar multiplication. I'm hoping you'll find this really easy, relaxing, maybe even enjoying the numbers, thinking, you know, this is going to allow me to solve harder problems. But more practically, being easy, it's going to help you ace that quiz when we come to these questions. So scalar 3, basically 3 times A, is equal to, well, we just multiply each element by 3. I get 24, 3, 15, and 12. Scalar multiplication. Building your confidence, building your abilities to do more. We can add arrays, we can multiply them, and then combinations. Here I'm just doing a scalar multiplied by a negative number. Well, negative number is no big deal. I'm going to get a negative 2 times everything in there. Well, that becomes a negative 8, negative 2, negative 6, and a negative 4. So scalar multiplication, scalar will by any value, negative or positive. The name I give to the array, it's my choice. Usually I try to make it match something that's related to the first letter in the meaningful application. Now we're doing just a little more complicated. We're adding scalar multiples and adding. We're looking for 3a plus 2b, right? That's scrolling. 3a plus 2b. I'm going to blame it on the recording software. 3a plus 2b. All it is 3a plus 2b of each element of A and each element of B. So just to make it really super clear, I'm just going to write it out in pieces. Even though I could probably do it all in my head, let's do 3 times 1 plus 2 times negative 1. Let's just write it out carefully so we don't mess up, especially when you have negatives in there. It's so easy to mess up. So we get 3 plus 2 times B, or plus 2 times negative 1. I'm going to put the negative 1 in parentheses, and that becomes 3 times negative 2, negative 6, plus 2 times 2, plus 4. Oh, zeros are nice. That becomes 0 plus 2. That's that first row. See if I can get my 2 in there. 2. Next row, 3 times A, 0. 3 times 0. Plus 2 times B, well, that's a 2 times negative 3, so I'm doing a minus 6. I'll write that. I'll multiply it out there. 3 times A is negative 3. That's the middle one. That's 3 times negative 1. Plus 2 times B, well, that becomes a negative 6. 3 times A in the row 2, column 3, that becomes a 6. Plus 2 times B, plus 4. Third row, 3 times A is 12. Plus 2 times B, I'll just add the 0 just to make it clear that B here has a 0 there. 3 times A, 9. Plus 2 times B, plus 2 times 1 is 2. 3 times A is negative 18. Plus 2 times B, that becomes a negative 8. When I'm doing multiples here, it helps to write out the work because I can easily mess up, especially with those signs. Check, and you can always go back and check. Yeah, 3 minus 2. And now do the final multiplies, or sorry, the additions, and then I get my final answer. Let's see, 3 minus 2, 1, negative 6 plus 4, negative 2, 0 plus 2, 2, negative 6, 3 minus a negative, negative 3 minus 6 makes negative 9, 10, 12, 11, and negative 26. Now I'll rely on you to check my answer. Does that look like I got the right answer? I could easily have messed up. When you're doing this, you can do it on your calculators, but on the calculator it is a little messy. But you can do array arithmetic on your programmable calculators. And maybe I'll have to check with Carissa if they spend time doing this on the calculator, because it's a little complicated on the calculator, and I don't want to confuse you if they don't do it in the other classes. But you can feed these numbers into your calculator and let your calculator do all the work, just like you can let Excel do the work in your Excel spreadsheets. I'm wondering, maybe showing you on Excel, because that leads to more practical understanding of Excel and how that can be used. But I'll talk to Chris about that. But for now, I don't think in the textbook and in any of your quizzes you get any bigger than a 3x3. So if you can do it on a 3x3 by hand, you're basically exercising your problem-solving skills and understanding matrices. Any troubles with getting these numbers at all? You're all good? Before we do products, let's see, did we get everything on this practice worksheet? Yeah, I kind of threw the multiplication at you. Well, what do you think? Do you think are you comfortable enough with adding matrices together, adding and subtracting? You good? Okay. Because the next thing does get a little more complicated. It's a step up. All right. Let's do it because we actually did it in that first problem. Let's see if we can do it, and then we can even next week. Actually, we'll be ahead of ourselves. We can actually do a little better practice and get a better understanding of it. The multiplying part is where the power really comes in. But it does get a little confusing because you have to multiply things out in the right order or it won't work. Let's see what they mean by that. When we're multiplying a matrix, when they're square matrices, multiplying is really easy. But when they are not quite the same size like we have here, let's start with a simple one. Before we come to a 2 by 3, let's do a 1 by 2 and a 2 by 1. Let's just come over here and let's do an example of a smaller matrices, and then we'll come to something larger. When I'm multiplying an array, say I'm going to do this array, 1, 2, multiplied by an array, a column of array, 3, 4. I have a column array multiplied by array. This is the rules of multiply for every array. For every row here in this array, remember the RC rule, I multiply by the corresponding numbers in the column of the second array. And then I add them together. So let's look at what that looks like. Multiplying these two arrays together means I'm going to get an array that has a 1 times 3 plus a 2 times 4. And that becomes 3 plus 8, 11. A 1 by 1 array. So that's 1 row, 2 column, multiplied by a 1 column, 2 rows. That is allowed. But I cannot do this. 3, 4. I can't multiply 3, 4 by 1, 2. The rows, the number of columns in this row, in this array, has to match the number of rows in this array, or I can't multiply them. The columns in the first one, the one on the left, has to match the number of rows on this way. Actually, will that one work? 3 times 1 gives me 3. Actually, this one will work because I do have 1 row by 2 columns, 2 rows. So I have a 2 by 1 multiplying by a 1 by 2. The thing is, I get a different size array in the result. That's the thing. When I multiply this way, I get a different result. I get 3 times 1, and then I get 4 times 2, 8. And it is a 1 by 2. It becomes do this again here. 3 times 1. Oh yeah, it becomes a column array. But let's do this 2 by 3 by a 3 by 3 example, so I don't mess you up, getting you confused. Let's look at an example here. There we go. Again, they give you the abstract form. I prefer putting numbers in there to be less confusing. But see what they do? A11 gets multiplied by B11. Becomes that. A12 gets multiplied by B21 and becomes this. A13 gets multiplied by B31. And I add them all together to determine what goes in my 1 by 1 array. That's the number that goes in that array. And that was when I did this multiply of the first row in array on the left. This is what they do in that first step. They multiply this row by this, giving you a value here that's going to be row 1, column 1 of A times B. So row 1, column 1 is going to be this whole row multiplied by this whole column and add it together. Going to give me one value, and I'm going to get another value for that row by that column, everything added together, and another value there. And they show you then, as they do all that multiplication, you're going to end up with a 2 row by 2 column array with all those things multiplied, added together across the row and column. Now they have all these numbers multiplied and added together. But remember, this is going to end up being just one number in this location. So let's go over that again. Figuring out a row by a column is the key here. Every row here, no matter how many rows there are, the position of the result, if I go back to that top where I drew those circles, where did that go? Right there. For every row in the array on the left, it gets multiplied by each element and added together. That becomes something in the first column, first row. So I'll call that, should I call that row 1 times column 1. This is going to become row 1 times column 2. The element's going to go there. Row 1 times column 3, going to go there. Then row 2 times column 1. Row 2 times column 2. Row 2 times column 3. And the resultant array is going to be 2 row by 3 columns. So we're multiplying a 2 by 3 by a 3 by 3, following the rules that the number of columns has to match the number of rows. My result becomes a 2 by 3. So those outer numbers become the resulting dimension of my multiply. For this one, I found when I was first doing that, I definitely had to go through some examples, or it's very confusing. Working through some examples of using real numbers will help this cement this in my understanding of it. But remember, all we're doing is row by a column, piece by piece. That's row 1 times column 1. Row 1 times column 2. Row 1 times column 3. Row 2 times column 1. Row 2 times column 2. Row 2 times column 3. in any array. So let's look at a practical example of actually using it. We'll come back to the associative and distributive when we're multiplying arrays. Let's see, do I have a practical example here? Let's just do one. Example 6 coming up here. They gave us square arrays. Okay, I'm happy to work with square arrays. They're probably easier and they're small. Let's do this multiply out. And for this one, for the first time through, let's show the work just to make it clear. Okay, upper left. First row times first column. So let's just write that out. R1 times C1. Well, that becomes 1 times 5. 5 plus 2 times 7. Row 1 times column 2. 1 times 6. 6 plus 2 times 8. 16. See where I got that? 1 times 6 plus 2 times 8. Now, row 2 times column 1. 3 times 5, 15. Plus 4 times 7, 28. And then row 2 times column 2 becomes 3 times 6, 18, plus 4 times 8, 32. And now let's put them in the, let's solve that. That's 19, 22, 43, and 50. Row times column, and then times that next column, this row times that column, and then that column. Takes a little practice. And I'd practice on 2 by 2 arrays. Little by little, they'll build up the sizes. But if you get that down, the row multiplied by the column, RC cola, multiplying the two together, isn't as confusing. I will upload this recording and practice. Read through the textbook. Practice through the textbook. And there's plenty of YouTube videos out there. If it's at all confusing, you can choose your style of teaching, how fast they go, what their voice is like. There's thousands of algebra matrix videos. Because it is a step up in all the math part. But it's a different thing than logarithms. Here's a way to multiply chunks of numbers that can solve some really hard problems. All right, we'll stop there. Turn in